changes title actually.
Yes.
No,
We'll tell it.
it's
I'll show
in
you.
the same title.
No, it's not.
No, the
I
same
can read off. I can read off my computer what the title was, but that's fine actually. That's fine. So the title today, you all can read it: Semi-classical analysis of magnetic Schrödinger operators. Well, Bernard, we're all yours.
Okay, so thank you very much. In this talk, I wanted to, at the end, to present a result obtained with Yuri Kordyukov, Nicolas Raymond, and Sandrine Gok. But I thought also that it was maybe useful to recall a few old results. So I didn't know what was the audience, and so maybe for most of you, you have already heard a lot about this. So maybe I will try to go faster for the beginning in order to arrive to the end, which is not clear. So this is not directly related to the program, but except maybe that, for example, my collaborator Yuri Kordyukov comes with questions about gaps for Schrödinger operator with periodic magnetic field. And after a few years, I convinced him that the first thing to understand is the case of one well, and then control the tunneling effect, at least for rough results like existence of gaps. The main thing to do is to analyze this kind of problem. Okay, so now I have to understand how it works. Okay, maybe, yes, this. Okay, so I will go very fast for this because this is, I hope, more or less standard notation. So I would like to analyze the Schrödinger operator with magnetic field. So all the questions can be asked in any dimension, but at the level of accurate results, I will essentially speak about 2D and 3D. Okay, so the general questions we want to look at is considering some self-adjoint realization of this harmonic Schrödinger with magnetic field. So typically it's either Rn or an open set omega in Rn. In this case, we can consider Dirichlet or Neumann. In my talk today, let's think that I will essentially speak only of Dirichlet. And so, of course, you can ask similar questions on manifolds. I will not enter too much in this direction. So the general questions are determine the structure at the bottom. At the bottom of the spectrum. So are there gaps? So typically one possible question, assuming that the operator is with compact resolvent, is to determine the gap between the first eigenvalue and the second one. And another problem is to, if you want to get final result, like tunneling, is to find an effective Hamiltonian who permits to analyze this kind of thing, or at least to guess what should be the result. And for this second part, at the moment, there are very few results in the pure magnetic situation. Okay, so I start to recall the completely standard cases. So the constant magnetic case, so you have the Landau level in 2D, and in 3D, so the bottom of the spectrum is, so if H times the module of the magnetic field. So I go rather fast on this. I just mentioned two, starting from this operator with constant magnetic field, two situations of I used the word perturbation in the previous slides, which is not completely correct because this is not at all a perturbation. But so this first example is oh, sorry. is come back to the analysis of Schrödinger operator with Jostrand. So in the case with magnetic field, and so here you. Oh, sorry, I am confusing between the two things. Okay, here I have to put. Yes, here. So this was the Schrödinger with constant magnetic field, and I had the potential. So in this case, it's not a total perturbation. In fact, this is the well created by V, which is quite important because this is at this minimum of V, assuming that V has a unique minimum, that everything is concentrate. And what do you do? At least to start with, you do the so-called harmonic approximation. That is, you replace V near the minimum by the quadratic approximation. And then you get this model. And you get that the ground state, lambda 1 of H, is alpha, some constant alpha times H. So I was saying that this model appears already quite at the beginning of quantum mechanics. Okay, so second example, now I take a much smaller perturbation, I take H squared. So here you can consider that it's effectively a perturbation. Then you can do a pseudo-differential analysis. And what appears is that if you want to understand the spectrum, modulo some error, you have to quantize this potential V of xy. That is, consider this function on R2 as a symbol on T star R. And near the first level of the Schrödinger operator with constant magnetic field, so the first Landau level, which is H, then the spectrum is given by some pseudo-differential operator, VW. W means the Weil quantization of the symbol P here, or the symbol V here. And so it's a H quantization, so the small parameter is written here. And then you can also compute a second term if you want a more precise result. So, okay, I think that's all for the model where you have an electric potential. And I would like today to speak mostly about pure magnetic effects. So there are no electric potential, and we want to understand how is the spectrum. And we will consider in some sense, the most generic situation, which is that that we assume that so the magnetic field does not vanish, and so we have this quantity, assuming say. So my omega will be usually relatively compact in R2 or in R3, except if I want to analyze toy models for which we naturally meet problems in R2 or in R2 plus. And so here, if you have, say, if you want to analyze the Dirichlet, the spectrum of the Dirichlet realization of the Schrödinger operator with magnetic field in some open set omega, there are two natural quantities which appear. So the infimum of the norm of the magnetic field, and maybe also the infimum over the boundary of the same magnetic field. Sorry. Okay, so the first very rough statement is this one, that if you want to get the lowest eigenvalue for Dirichlet, then this is simply h times the infimum of the norm of the negative. Okay, so this is rather easy. I will write later for the lower bound the inequality which gives that, and for the upper bounds it's easy to construct Casimodes, which gives you the right energy. Okay. I just mentioned for one slide the case of the Neumann problem. And in the case of the Neumann problems, the situation is quite different. And the analysis of Neumann, the Neumann problem is strongly motivated by, yes?
The D should be an N then, right?
Yes.
Or lambda 1.
Yes, N,
Okay.
yeah. Yes. Neumann, yes. Lambda 1, Neumann. And then you get so before you can think it was infimum of B and B prime, which is the same as the infimum of B. But here you get infimum of B and theta naught B prime. And theta naught is some explicit spectral constant between 0 and 1. So what does it mean? And that means that the boundary effect for the Neumann problem could be the most important. In particular, if you assume that the magnetic field is constant, then you have B equal constant equal B prime, and so this is this term which gives you the lowest energy. So what does it mean? It means that in this situation the ground state is living at the boundary. So this is what was called in the context of superconductivity, this is called surface superconductivity.
And this theta naught is an absolute constant, or it depends on something?
Theta naught is just the bottom of the spectrum of the Schrödinger operator with constant magnetic field equal to 1 in the half space, with Neumann condition. And there is another one-dimensional interpretation. So it's natural that it's lower than the Dirichlet case. This is Neumann, and this is strictly less.
So
this is
this is an absolute constant.
It's not.
No,
Please?
not.
Wait, it could depend on. No.
On what?
No, it's
No, it's
I
in the
think
half space, it's an
Just
absolute
the
constant.
constant.
Yeah, it's an absolute constant.
absolute constant. Okay. Okay, here I mentioned a lot of literature. Maybe I will skip and then arrive to the main subject in my talk. And so, in order to go further, I will consider Dirichlet, and I will assume that the boundary does not play any role. And the way to say that is to assume that the infimum of the norm of the magnetic field at the boundary is strictly larger than. So in this situation, the analysis of the ground state energy, or the first eigen, a lot of eigenvalues actually, is independent of the boundary, and it's the same to look at a global problem in RD. At least, so if you want to look at a problem in RD, you have to assume that you are in the same, basically the same situation. So you assume that the infimum of the module of the magnetic field is strictly less than the lim inf at infinity of the. In this situation, you will see that at least for h small enough, there are no difference. Okay, so in 2D, so in this case, the first situation is to assume that there exists only one minimum. There are more than one, so actually you can analyze the different cases separately. And I will assume also, that this minimum is strictly positive. So there are a lot of literature in the case where it vanishes, but this is not my aim today. And and I assume also that, so this is a generic assumption, that the minimum is non-degenerate. And so this is what I call in the title, in one of the titles, magnetic well. You have your magnetic field, which admits minimum. So in dimension 2, the magnetic field is just identified with a function. Okay, so here is a result which was obtained already with Moram in 2001, and with improvement in 2009. And we will see later other improvement. So, we have so what is the result? First, we get the terms corresponding to the constant magnetic field approximation, BH. You are the first Landau label. And then it appears a second term with H squared plus some error. And everything is computable. Theta 1 is A squared over 2B, and A is a constant. Okay?
So was this Dirichlet or Neumann?
Please?
Dirichlet or Neumann?
This is Dirichlet. But I have assumed that the boundary does not, that the magnetic field is higher at boundary.
It could be just going to infinity.
Yes,
Infinity.
same result
This is local.
if the infimum is less than the limit infinity. It could be also Neumann under the condition that this B is strictly less than this theta naught B prime. If theta naught B prime is less than B, then you have to look at the boundary. So all these problems gives the same result under the condition I have mentioned, modulo exponentially small term. So, but I will mainly describe here only result modulo OH infinity. So they are not sensible at all with, yes?
I mean, except for the constant BH, the second order term, right?
Yes.
You would get the same term if you replace the magnetic field by just the potential, which is obtained by the Hessian
Yes.
of
I will,
beta
I will
x,
arrive
x,
to
right? So
this.
it's just a quadratic approximation.
I will arrive to this.
It's just a quadratic
just,
approximation, right?
Yes, we
Yeah,
will
that's
see.
the theorem. Yeah, sure.
We will see that a Weyl quantization of the magnetic, like in the second example with V, when I add H square V,
Sure.
then the first term will be obtained by quantifying H, considering B as a symbol. This will be in the
Okay,
next thing. But so before just mention the most recent results obtained for this. So the recent improvements are of two types. First, obtain complete expansion, and secondly, treat not only the first eigenvalue, but a finite number of eigenvalue, fixed number, and also I will explain later. We can take J relatively large, that is control more than a fixed number of eigenvalues, and take a number depending on H. Okay, so once you have this kind of formula, you have in particular a control of the splitting between the first eigenvalue and the second one.
But where is the shape of the potential? The potential is
The shape of the potential is here.
only through.
Well, then everywhere, but for the first term.
No, but only the first derivative. So
Yes, but I have only written the beginning of the sequence.
okay.
Okay, so here, yes, effectively, for the free first term, you only see D, which is this determinant, A and B. A was defined in the previous slide.
But in the first terms of approximation approximation for the eigenvalue, you have very restricted dependencies on the potential only through some first and second derivatives.
Hmm? I don't understand your remark.
Okay, you
I
have a
assume that B
potential.
is infinity. I have not control all the derivative I need to make my approximation. But
Yeah, that's
except
what I'm
this,
asking, that you are kind of if you replace V by a parabola, it gives you.
There is no V. Point is that there is no V. There is only
I have no,
magnetic
I have
potential,
only
which is
B. Hmm? I have no electric potential.
there is no V.
So
Oh, okay.
so the message is that my electric
Ah.
potential is replaced by H times B. Hmm? This is
Just-
the,
Mhm.
Can you just blend in the next slide?
Maybe you can go back to H again. Okay.
In alpha J2, the D. Okay, yeah, okay. This is correct.
okay, so these are the previous
Yeah, this
slide.
was.
Can you
And
show
then here
H?
you have some eigenvalue,
okay,
some
okay.
harmonic oscillator that we will meet later.
Can you show H again? Maybe. Can you show the operator again?
Maybe you
Yes.
can write it on the board actually.
Okay. So
Write it
this
on the
is
board
the,
so we have it on the board.
oh yes, but yes. So maybe the sign is wrong, but dxi is 1 or dxj is 1 of I.
But what is A?
A is
A
the
is the
magnetic
magnetic
potential. B is curl A.
Yeah, but this is just how it depends on X.
On?
How it depends on X.
Ah. Yeah.
No, any, in fact, any. Parentheses.
Yes. Yes, some.
Yes, but this is my question, that when you write the asymptotic for eigenvalues, yeah, there is only,
Now I assume that B as a means, so take B positive in dimension 2. I look at a point where B attains the minimum.
yeah,
And I assume that it's a point 0, 0 if you want.
yes, but this what I mean, that all your asymptotic lambda J at the first term, they contain only values something like B and A, so they do not depend,
It depends on B and the Hessian of B.
yeah, so they depend only, if you imagine approximate your potential as a parameter, they depend on parameters of this parabola.
Yes?
Yes,
So
this was my question, so yes, it's the
No, but there is no potential in this operator.
No, she means the magnetic.
magnetic potential.
No, but the magnetic potential doesn't look like that. It's the magnetic field, meaning the curl of the magnetic potential that looks like a parabola. This is what looks like a parabola. You see the B, exactly, but it's not
Okay,
B.
sure.
B is not the
No,
parabola.
but
It's not
this
E.
is what I
So the
meant.
result
Sorry,
is
I
obtained by
missed
taking
this.
B, we will see most clearly this
From
point,
B, you,
B plus the quadratic approximation of
yes, the first term depends on the quadratic approximation. of
Yes.
B. Yeah.
not only the first one, but there are more than the first one.
Can you find that number?
You see,
Because H
first one B, second one 0,
smallest
third one depends only on the Hessian. And so this is only starting from the third one, the fourth one that you will meet.
Other derivatives.
Okay.
Magnetic potential. The magnetic field.
Okay, so here it's the answer to the question of Frédéric. So, but at this moment, before we work more recently, this is just by comparison that I say that. I see that looking at the Weyl quantization, so this beta hat is related to a change of variable we'll describe more precisely what is this change of variable. So at least you see that if you quantize this, if you add some term of this type, then you get the two first terms of the asymptotics. But this was not obtained like this at the time. Okay, so now you have the answer to your question. Here is a model that gives you the bottom of the spectrum, the two first terms. And so for the first approach, we were just trying to control Quasimodes, and we look at this model and try to understand what's going on, and then we go further. So what is for this kind of model, what replaced the so-called harmonic approximation? What replaced the harmonic oscillation, the so-called harmonic oscillation, is to have a blowing up argument. So you write x equal h1 half s, y equal h1 half t. So h arise in factor, and then you get this model. And then the idea is that you do what we were doing when you give your first course for Schrödinger with constant magnetic field to get the spectrum. So you have different things to do. First, a partial Fourier transform, and then a translation. And so now you get as main term your harmonic oscillator, and then the other terms arise as errors. And then and then you construct Quasimodes by looking to u0 of s times phi of tau, and then go on. And so the first harmonic oscillator is there, and there is a second harmonic oscillator which appears, which is obtained by projecting, if you want, restricting L1 to the projection on the first Landau level. This gives you something depending only on the variable tau, and the computation, the computation of this operator gives you an harmonic oscillator in the tau variable. And so this explains in the formula this thing. That is, the J corresponds to the level of some harmonic oscillator, second one. Okay. So this is the first thing. So how to get improvement? And so independently, not completely independently, because we discuss a lot together, but at least we follow two different approach. One was to push this idea to construct a Grushin problem, and the group Raymond Sandwingok was trying to use the idea to find a Birkhoff normal form. And so as you will see at the end, this is the Birkhoff normal form who wins at the level of the quality of the result. But let's explain first maybe the part I know better, which is the approach of Grushin problem. So there are various things in the proof we gave, and the idea was to find. Till now, I say I have seen that comparing formulas is the same as the pseudo-differential operator. So the point was how to prove it through the construction of these pseudo-differential operators. This is different to compare to models. And so I want to explain how to get pseudo-differential operators in one variable who gives effectively the complete asymptotics. Okay, so there will be a change of variable, a normal form near a point, so the minimum of the magnetic field. Sorry, I have always the same problem with this. And then construction of a Grushin problem. Okay, so the change variable is very simple, and the idea is to find new coordinates in which the magnetic field becomes simply dx1 exterior dy1. So in these new coordinates, the symplectic form, the natural symplectic form in R2 is exactly the magnetic field. And so this is the idea behind the change of variable, but in any case, it's very explicit. First, by your gauge transform, you arrive to A1 equals 0, A2 equals A, and then the new change of coordinate is just this. So second step, so we do again what we have done before. That is change variable, gauge transform, partial Fourier transform, and at the end a dilation. And then we follow the operator that we have. So at the end we get a new operator that we can write in this way. And so what is t tilde 0? So this is a function b2 derivative of a with respect to y square. And here you see some pseudo-differential quantization, but these two operator commute. So I keep let's see, no, yes, I think yes, it commutes. dxy plus, this is my, after this transformation, so gauge transform, change of variable, partial Fourier transform, I get this operator, which is now written as a pseudo-differential operator. Now, how to construct a Grushin problem. So the idea behind the construction of a Grushin problem is that in order to analyze the spectrum, it's easier first to construct an isomorphism, and then to recover so something which will be invertible, and then to recover the spectrum indirectly. This is also close to the so what is Schur method or what was the third name? The Feshbach. Okay. So the idea is to start from a very simple model. So you remember when we do the starting point for the analysis, we have this harmonic oscillator in one variable. So we want to look to the spectrum close to B0H. So everything is divided by H. And so I make the problem invertible. So what do I add here? A projection on the first eigenfunction. And here I take simply the adjoint of R. And this new problem is invertible. So I write it in this way, and here this is the inverse of this problem. It has the same structure, but now the object, which is here, is a pseudo-differential operator on a reduced L2 of L1, only one variable. And at least formally it's easy to see that Z belongs to the initial problem here, to the spectrum of this, if and only if 0 belongs to the spectrum of this. So it's not completely correct, but I think if you want that the dependency with respect to Z is this way. This is not exactly the correct, but you can reduce to this. And so, so what is the result of this is that in order to understand the spectrum of the initial problem, you have to analyze the spectrum of a one-dimensional pseudo-differential operator. Okay, so this kind of analysis is rather standard, at least for the Sturm-Liouville problem, because all the answers are now given by the Bohr-Sommerfeld rule. So the only difference is that you have to work with a pseudo-differential operator in 1D. But so you see that you have much more than the harmonic approximation at the bottom. You have a pseudo-differential operator, and you can also consider more excited states in a suitable assumption. Okay, so this is the the idea. This is the idea in one direction. In the other direction, how you construct Quasimodes. Then you look again to the same system, but you take the right inverse instead of the left inverse, and then it's rather easy to construct in this formalism a Quasimode. Okay, so this is this method, the so-called Grushin method approach. So the improvements are not only to get a finite number of eigenvalue, but you see that you get a little better. Okay, so I think now the second approach by Nicolas Raymond and Sandrine Gok. I think there were at least former discussion with what is I don't remember his first name. There are many Frédéric Faure, yes. So Frédéric Faure, Nicolas Raymond, and Sandrine Gok. And if you are a good reader of Ivry's book, Ivry's evaluating book, you can find also this kind of statement in any version of the book, but with the same misprints in any of the version. And so it's difficult to decide if one can consider it's correct or not. Okay, so the idea is now we start from the symbol of the Schrödinger operator of a magnitude. So yes, the notation are more or less the same, except x1, x2 is xy here. I will change of notation most of the times, I'm sorry. Okay, so we start from this, and then first you do classical mechanics. And so you try to find symplectic diffeomorphism which simplify the form of the Hamiltonian. So in the previous approach, I was just working with the beginning of the expansion. I was just trying to take a normal form for the first step, and then I was pushing my expansion. Here I tried to do a little better, and so this is the classical Birkhoff normal form, which consists in saying that there exists symplectic diffeomorphism. So this is local near the minimum of. It's semi-global. So you have the surface energy, the zero of the symbol, h equals 0, and then in the neighborhood of h equals 0, so you will send h equals 0 on z1 equals 0. So I prefer to take a complex writing, and then the Hamiltonian becomes modulo of z1 square, and a function which depends only on z2, so the two other variables, and the modulo of z1 square, plus some error, which is O of modulo of z1 infinity. Okay, so and the small phi, which we meet before, is reappears here this way. Now, so this is the classical mechanic part, and then you have to find a corresponding quantum version of this. Okay, yes, I put the page for Ivry's book if you want to. Okay. And so the second part now is to quantize this. So now instead of finding simply symplectic diffeomorphism, you have to quantize it as a Fourier integral operator. And these Fourier integral operators should be essentially unitary. By essentially unitary, I mean that if I look F star composed with F, it's, no, U, say, U star composed with U, then I get the identity where modulo O of H infinity and where I am interested in. That means that you have to, at this point, you have to know already where you are interested to work. And for example, if you look at eigenfunction of HU equal lambda U, you have already to use the information that you have on the so-called H wavefront set of the eigenfunction. Now, the form that you get is very nice in the sense that this operator is unitary equivalent modulo this remainder to a very simple expression IH. This is my one variable harmonic oscillator, and FH. FH is a classical H pseudo-differential operator which commutes with IH. So I think so there are two. This is the same object here and here. My cat and okay. Now, what it means here is that if you now restrict the operator to the first to the level, so the first Landau level that is relative to the first eigenvalue of IH, then you will get a pseudo-differential operator in the two other variables, the x2 variables, and and so the okay, I destroyed too many things in the slide. So now, if you look to FH restricted to the first level of IH, you get the pseudo-differential operators, which will give you the spectrum of the operator, at least at the beginning, because you have to avoid to meet the second eigenvalue of IH. So you have a region between H and 3H where the spectrum is given by the restriction of FH to the first eigenspace of IH. And so this is a pseudo-differential operators, and same remark as before. You are reduced to the analysis of a pseudo-differential operators, and you can use both on a third. So that's what I wanted to say about this. And now, what about 3D? So here is the toy model. So this is the first thing to do if you want to understand something, is to try to look at this. So and for this, you can construct Casimodes by playing in the same way. And what you meet successively is now 3 successive harmonic oscillators. So in the different steps, you will meet 3 successive harmonic oscillators. And so I will try to explain a little how you can get it by using this normal Birkhoff normal forms approach. Okay, so I have a quota of an hour, so I will try. So I'm sorry to change a little the notation, that I was taking another file. So now we play with Q and P instead of X, XC. So we are in dimension 3. Our problem is symplectic, but we are just in the case of R3 cross R3. So, okay, and then we have our Hamiltonian, the magnetic potential alpha that I prefer to described as a one form, and then the magnetic field that you can consider either as a vector in R3 or two forms in as you prefer. Okay, so sigma is the zero set of H, and then you can parameterize very naturally sigma by the map J of Q, which is Q gives QA of Q, and with this rule, you can recover the magnetic field as the inverse J star of the omega naught. Okay. Now, so we would like to do the same semi-classical analysis. So the first remark is that, so in dimension 2, it was rather easy to obtain an Hagman estimate by just simply, so I recall that you can here assume that B has constant sign if B does not vanish. And in this, there was this very simple estimate which permits to start with the control of the decay of the eigenfunction. In dimension 3, so this is almost the same thing, but you are obliged to assume some control of the variation of nabla B. So you cannot obtain the same kind of estimate without to add some information about the oscillation of B. Of course, if B has components with constant sign, there is enough. This is very easy, but you have to control, if you want, statements. Starting from dimension 3, you have to control at least one derivative. Okay, and under this assumption, you get something which is quite close to the previous, the 2D inequality, except that you lose a little as H tends to 0. Okay. Then for the bottom of the essential spectrum, you get essentially H bar B1. Sorry. Modulo some small error. Okay. So now the second, so there was first assumption here. So I assume that B of Q is strictly positive, and some control of the derivative. And then my magnetic well assumption is that B naught, which is the minimum of B, so there is a small change of notation in comparison with the beginning of the talk. So B is a function of Q now, and B naught is the infimum of B. I assume, to simplify, because in the proof you can start the different steps by a weaker assumption, but I will assume that B has a unique minimum at one point Q naught, and that this minimum is non-degenerate. Okay. Okay, so there are two things that you have to know a priori. First, you have the standard semi-classical result that that you can localize the wavefront set by looking to H, the zero set of H. So everything is localized near the characteristic set. And the second one is the so-called Hagman estimate, so which is finer in the sense that it says it involves the second term, the sub-principal symbol HB, that is for the decay of the eigenfunction close to H infimum of B, the potential H times modulo of B plays the role of an electric potential, and the decay of the eigenfunction can be computed using this function. And so this is important to mention these two properties, which permits to justify the control of the remainders. Okay, so now we do the standard job to find symplectic coordinates. We make sigma now it's a three-dimensional surface, and we choose coordinates such that sigma is given by x1 equal psi1 equal psi3 equals 0. And then here is the normal form that you can get in dimension 3. So this is the first step. So in the first step, we should meet first a first harmonic oscillator. But in the other variable, you have just the symbol of pseudo differential operator. So this is without to mention this, the technical reason my initial h is now h bar, and so new h will appear after. And so this is LH bar A, this is this operator in dimension 3. And so here is the form that you get. You can, via a Fourier integral operators, which is unitary, conjugate LHA to a new operator, which is the Weil quantization with respect to h bar of this n h bar, which is an operator valued symbol depending on x2, xi2, x3, xi3. And I have now make for the variable x1, xi1, I have replaced x1, xi1 by, sorry. Okay. I have replaced x1, xi1 by this use first of the classical Birkhoff normal form and then the quantum one. I can replace this x1, xi1 by just the operator IH bar, which is the harmonic oscillator in one variable. So this is the first normal form. And so if you want to understand the spectrum, the first thing is to choose, if you are interested in the bottom, but everything works well for the bottom, and if you take excited state of IH bar, you will, so maybe you keep your Casimodes, but you lose the control of the spectrum because there are a mixture between different. So in order to continue, what do? You will replace the operator, which is here, by its value on its first eigenspace. That is, you replace IH by simply H bar, and here H bar. And so in this way, your spectral analysis is now obtained by looking at this operator. So this is first reduction. So now I have a new operator in 2D. X2, xi2. So this is the Weil quantization, and here I have written the symbol, which depends on 4 variables: x2, xi2, x3, xi3. Okay. Then I continue. Now I look to the. So where is this B? Yes, it's here. So if you want the first time, you look at the quadratic approximation of B, and then you do so with x3, xi3 as parameter, and then you will try to do the Birkhoff normal form with respect to these 2 variables, x2, xi2. Sorry, it was sorry. No, sorry, I do it first with respect to x2, xi2 fixed and with the variable x3. And so here x3 gives b of x2, xi2, x3. So admits a unique non-degenerate minimum. So I have made an assumption at the beginning, a much stronger assumption. So at each step I only need one partial transversal non-degeneracy, but Yes, 5 minutes. Okay. And then, so I do again the same job. And now the new model, here I see the second harmonic oscillator, psi3. So the symbol is psi3 square. Sorry. Oh, I'm lost. First, vector form. Yes, here. So now you see that this is a new harmonic oscillator, but there is a new quantization. Here I get an harmonic oscillator. Oh, sorry. First, sorry. Okay. So here I see that there is a new semi-classical parameter which appears naturally. It's no more h bar, but it's h bar 1/2. Okay. And so in order to continue, I have to think for some time that I'm working with h quantification. So in this picture, and this explains why we get powers of h1/2. In the second picture, we meet a new Planck constant, which is instead of h bar, it's h bar 1/2. And then you play the same game. You will replace you will take the first level of the second harmonic oscillator and replace it by your h. And then at the end, what do you get? You get a new pseudo-differential operator, but this time in one variable. And then either you play again the new normal form to get the last harmonic oscillator under suitable assumption, or you use, as I said, Bohr-Sommerfeld rules for the spectrum at the bottom. So I just wanted to finish by giving some statement at the end. Okay, so this is the last normal form with the last harmonic oscillator. And then the kind of result that you can get, there are still mistakes, is this kind of thing. So first, for any c in 0, 3, then you can consider all the eigenvalues which are less than this. So there are a lot, because there are of order h minus 1/2. And then for all this eigenvalue, I can give an expansion, which is a remainder, which is uniform for m in this. So this h is h bar. I'm sorry, I tried to correct. Everything here is h bar. Okay. So this is the kind of things that you can get. If you compare with what we get with Kordyukov by Casimir, first we get only the upper bound, and we get only a finite number of eigenvalues, finite independently of h bar. So this Birkhoff normal form approach gives you a lot of new cases. And this 3 corresponds to the second level of the second harmonic oscillator. So I can only see correctly the spectrum below the second level of the second harmonic oscillator. So I'll stop here. Thank you.
Thank you. Are there any questions or comments? I have a question actually, but it's let's go back to 2 dimensions, right?
Yes.
So imagine that you have well 2 minima, right?
Yes.
That of course take the same value, right? Not only local minima but global ones,
Okay.
where the magnetic field takes the same value. As you have some kind of Agman distance that is coming into play, can you say something about tunneling? I mean, do you get?
I don't have
But you said you have Agman estimates, right?
I have some Agman estimates.
So, but these Agman estimates,
nothing says that
but
it's optimal.
these are just local, right? Around
Yes.
minimum. So there are
maybe
you don't have a control.
there is some hope to have a beta of one variable which will give the tunneling between the two.
Exactly.
But you need to have some control of the construction with two minima at the same. It's not.
Yes, but can you
it's-
follow? Can you?
It's
I mean,
not
if you look
completely
at
impossible.
if you look at the natural Eigman distance you'd expect in this case, right? What kind of assumptions do you need on the magnetic field to be able to do the same kind of analysis that you did about 30 years ago with your
For this kind of question, there are recent contributions by Bonaï, Hérault, and Raymond. I don't think for the moment they can attack this case, except assuming toy models where there are additional separation of values.
even in 2 dimensions.
But,
we
yes.
stick to 2 dimensions.
So the case, there are 2 cases where one is quite close to, at least to propose an answer, which is not proven, but just give the candidate to be the formula. It's the case of Neumann problem for Schrödinger operator. In the case of domain omega with like typically an ellipse.
Okay.
There are 2. So in this problem, the localization is near the point of maximal curvature.
Okay,
And
so
you
you're
have
assuming
to-
here,
and
you're
you-
assuming here the magnetic field is constant, right? So you're taking
Yes,
constant magnetic
constant
field on the
magnetic
ellipse.
field.
Okay.
And Neumann,
Okay.
and two points
Okay.
of maximal curvature which are related by a symmetry.
Okay.
Then there is a Casimir construction by Bonaï, Hérault, Raymond, where you can effectively get WKB
Okay.
type solution for which you can see the decay.
Okay.
So you have a candidate.
Mhm.
What is not done, to my knowledge, is the proof that the eigenfunctions are close to this, the WKB approximation.
Okay.
But you have a formula. There is another case I have analyzed with Kashmar, consists in looking in the Steklov, something related to the Steklov problem, the Robin problem, where we have the same kind of things. That is, we can produce a sufficiently good WKB approximation, which permits to guess what should be the turning.
Okay.
For this model, to my knowledge, no, we don't know. But it's clear that there are almost no result about purely magnetic tunneling measure of the tunneling effect. And I think for the moment, the result I know are just rather preliminary in the sense, if we find a good Casimir which permits to guess what should be the tunneling, it's already very good. I have not written any Casimir of this type, so for the moment I am modulo O of H infinity. I am more doing
Sure.
harmonic extended harmonic approximation that's writing WKB solution.
Are there any other questions or comments? Well, if not, let's thank the speaker again. And, we will another seminar tomorrow at the same time, 1:30 in the same room, right?
The speaker
but
is
you
not
go-
present. The speaker is not the same.
No, the speaker is not the same. But you go first, yes, I added.